Good morning, middle two students. Today we're going to revise what we have covered during the period from the second term till the 15th of March. We have studied Unit 1 and Lesson 1 in Unit 2. Now we're going to start with Unit 1. Unit 1, periodic motion. Periodic motion, it's divided into two lessons, oscillatory motion and wave motion. The first time, I'd like to define periodic motion. It's the motion which is regularly repeated in equal periods of time. Examples for the periodic motion, we have oscillatory motion and we have wave motion. Lesson 1, which is talking about oscillatory motion, we have studied the oscillatory motion, and we said that the first and clear example for the oscillatory motion, the sample pendulum of the clock. We have a lot of examples like the swing, like the stretched spring, and so on. And we said that the oscillatory motion, it's the motion of an oscillating body as it passes by a fixed point, it's the motion of an oscillating body which moves around its rest point in equal intervals of time. So this is point A, the rest point of the oscillating body, and it moves around both sides of this rest point in equal intervals of time. Again, let's say the oscillatory motion, it's the motion of an oscillating body as it moves around its rest point in equal periods of time or equal intervals of time. We have some concepts related to the oscillatory motion, and we said that they are divided into four concepts. Number one, amplitude. The maximum displacement, the maximum distance reached by this oscillating body away from its original position is known as amplitude. So amplitude is the maximum displacement done by the oscillating body away from its original position. As we said that it's distance, so it's measured in meter or centimeter. Concept number two, complete oscillation. We said that the complete oscillation, it includes four amplitudes, okay? It includes four amplitudes. So it's starting from A to B and then back from B to A, then from A to C and from C to A again. So it moves, or it includes four displacement or four successive amplitudes, AB, BA, AC, and CA. Let's define the complete oscillation. It's the motion of an oscillating body as it passes by a fixed point on its path two successive times in the same direction. Periodic time is the time of making one complete oscillation, or time of that the oscillating body takes to make one complete oscillation. As we say that it's a time, so its measuring unit will be second. It's measured in seconds. If I'd like to calculate the periodic time, we know that the rule is the time in seconds over the number of complete oscillations. And we said, where we answered many problems according to this concept. The last one, which is frequency, and we said that the frequency is the number of oscillations or the number of complete oscillations done by the oscillating body in 1 second. Its sample is F, and it's measured in hertz, okay? If we'd like to calculate this frequency, we're going to make the number of oscillations or the number of complete oscillations over the time in second. As we notice here that the relation between the periodic time and frequency is inverse because we have the inverted rule. So multiplying the periodic time by the frequency equals 1. I'll say it again, the relation between the periodic time and the frequency is inverse. So if I'd like to represent this by this graph, frequency and the periodic time, it will be an inverse graph, okay? This is the summary of lesson 1. Lesson 2, which is talking about wave motion, we said that the wave is produced, let's say an example, if you have a stone and you throw it in water, so it will form some waves of water. These waves have the same center, or they are concentric circles. These circles have the same center where you have thrown the stone. So wave is the disturbance that takes place in the medium particles that propagate and transfer the energy. Wave motion is the disturbance in the medium particle, or this is the motion of the medium particles that transfers and transfer the energy in the direction of propagation. What's meant by the direction of propagation? It's the direction at which the medium particles propagate or transfer the energy. Types of waves, they are classified according to two ways. Number one, according to the direction of vibration of the medium particles. If the medium particles vibrate perpendicular to the direction of propagation, which means that they vibrate ups and downs, they are going to be called transverse. If the medium particles vibrate along the direction of propagation, they are going to be called longitudinal. Transverse wave is formed of some crests and troughs. some crests and troughs. Longitudinal waves are formed of some compressions and rarefaction. If I'd like to define the crest, it's the highest point of the transverse of the medium particles on the transverse wave. Trough is the lowest point of the medium particles on the transverse wave. Compression is an area on the longitudinal wave at which the medium particles with the highest density and pressure. Rarefaction at which the medium particles away, so this is an area on the longitudinal wave at which the medium particles with a small or with low pressure and density. Next, we can divide the waves according to their ability to propagate into mechanical waves and electromagnetic. And we studied them in the last year, and we said mechanical waves, they are the type of waves that need the medium to propagate, and they cannot travel through space or vacuum. The electromagnetic, they are a type of waves which can travel through vacuum and also in all media. Mechanical waves, they have a low speed or low velocity, but electromagnetic, they have a great speed, and we can say the velocity of light waves 3 times 10 to the power 8 meter per second, which can be 300 million meter per second. According to the examples for the mechanical waves, we have sound waves and water. Examples for the electromagnetic, they are like light, radio, and so on. Mechanical waves can be transverse or longitudinal, but electromagnetic are all transverse. Next, we have a live application for these waves, like physiotherapy treatment or the jacuzzi, which is used to treat some sprains and cramps by using hot water, and nervous tension using cold water. It depends on the movement of the waves, wave water or water waves in a circular way. So we can use it in our daily life, and this is the live application for the wave motion. Next, we have some concepts related to the wave motion. If you would like to compare them with in the oscillatory motion, the first one here, wave length. Wavelength can be for a transverse wave and can be for a longitudinal. Wavelength for the transverse wave is the distance between 2 successive crests or 2 successive troughs. Also, as it's a length, it's measured in meter or centimeter. The wavelength for the longitudinal wave is the distance between centers of 2 successive compressions or 2 successive rarefactions. Again, centers of 2 successive compressions or centers of 2 successive rarefaction. Also, it's measured in meter and centimeter. Number 2, the amplitude. As we said in the oscillatory motion, it's the maximum displacement done. Here it will be the maximum displacement, but achieved by the medium particles away from their rest points. Here, amplitude, maximum displacement also is measured in centimeter or meter. Number 3, velocity. Velocity, it's the distance covered by the wave in 1 second. As it's distance covered in seconds, so it's, we can calculate it by making the distance over time. And its measuring unit is meter per second. If I'd like to say the velocity can be the same velocity in all media, no, it differs from one medium to another. For example, the sound differs, or the sound velocity differ from being in air, as it equals 340 meter per second. It can be in water 1,500, and it can be in wood 1,850 meter per second. So it differs from one media to another. Number 4, frequency. As we said in the oscillatory motion, it was the number of complete oscillations in 1 second. Here it will be the number of waves produced in 1 second. It's also measured in hertz, kilo, mega, and gigahertz. These are the fractions for the frequency. And the last one, we can find a relation between wavelength, velocity, and frequency, and this is known as the law of propagation. Law of propagation, velocity here, it equals frequency times the wavelength. Here, velocity is measured in meter per second, frequency hertz, and the wavelength is measured in meter. Thank you so much. Now we're going to start in Unit 2, Lesson 1, Properties of Sound Waves. What's meant by sound? Sound is an external factor that affects the ear, causing the sense of hearing. How is the sound produced? Sound is produced due to the vibration of the medium particles. and also it stops when this vibration stops. What is the nature of sound waves? Sound waves are mechanical waves because they need the medium to propagate. They are longitudinal waves because they are formed due of some compressions and rarefaction, and these waves propagate along the direction of propagation, or the energy of sound waves transfers along the direction of propagation. We can hear sound from all directions because sound propagates or travels in the medium as spheres of compressions and rarefactions. Sound velocity, as we defined the velocity before, it's the distance covered in 1 second. So the sound velocity V is the distance covered by sound waves in 1 second. If I said it's measured in meter per second, and also it can be calculated by making the distance over the time. If I'd like to say the sound velocity can differ from medium to another, yes, sound can be faster in solids, as it's 1850, and in water will be less than gases. It's higher in solid than, I'll say it here, solids, the speed of sound waves is solids greater than that in liquid, greater than that in gases. Properties of sound waves, as we said that we have here 3 main properties for the sound waves. Number 1, sound pitch. Number 2, the sound intensity. Number 3, the sound quality. Sound pitch is the property by which the ear can distinguish between the sharp and the rough sounds. Sharp sounds, they are like the man or the woman or the sparrow, like it's a bird, and the rough, they are like the man or even the lion. Sharp, it has a high-pitched sound, or it has high frequency. Rough, it has low frequency, and it can be called low-pitched sound. According to this, if I'd like to determine if it's if it has high frequency or low frequency, we said that we have a tool called Savoyard's wheel. We can use Savoyard's wheel just to determine the frequency of unknown tone. How can we use Savoyard's wheel? As we said before, we're going to rotate it till we get the same sound of the tone that you need to calculate its frequency. So by making the number of cycles and calculating the number of cycles and getting the time in seconds, and even knowing the number of gear teeth which is written on each gear of Savoyard's wheel, we can calculate the frequency of the unknown tone. I'll say it again. Frequency can be calculated by number of cycles that is going to be made by the wheel times the number of gear teeth over the time in second. And as we said before, that frequency is measured in hertz. This is how to calculate the frequency of unknown tone. Property number 2 of the sound, which is the sound intensity. Sound intensity is the property by which the ear can distinguish between the strong and weak sound. How can the sound be strong? If you beat a drum hardly, you can hear it with a strong voice, and if you beat it softly, you're going to hear that the sound is weak. What are the factors that affect the intensity of sound? We have here 5 factors. Number 1, the distance between the ear and the sound source. The distance between the ear and the sound source varies inversely with the sound intensity, which means that by increasing the square distance, the sound becomes weaker. So the relation between them is inverse. Number 2, the amplitude of the vibrating source. By increasing the amplitude of the vibrating source, the sound becomes stronger, and also vice versa. But if I'd like to say an example here, I have two figures. This is the amplitude of the first figure, and this is the second one. By increasing the amplitude, the sound becomes stronger. So it has strong sound, and this one has weak sound. Number 3, the surface of the vibrating body. We said if we have a resonance box or a wooden box, that can we put our mobile on, it will increase the vibration, so it will increase the sound. So by increasing the surface area of the vibrating body, the sound becomes stronger, which means that the relation is direct. And this, we have a live application, the violin, the guitar. We have a stretched spring on a resonance box, which is used to increase the surface area of the vibrating body and increases the sound intensity. Number 4, the medium density. By increasing the density of the medium, the sound becomes stronger, so the relation between them is direct. Number 5, the wind direction, which means that if the sound produced with in the same direction with wind, the sound will be stronger, and if it was in the opposite direction, it will be weaker. Property number 3, the sound quality. It's a property by which the ear can find the nature or can determine the nature of the sound wave even they are equal in pitch and intensity. Let's say an example, if I have a tuning fork and a piano, the sound produced from the tuning fork can be differentiated from the piano. Why? Because the tone produced from the tuning fork is known as fundamental, which means that it's sample pure tone. But that which is produced from the piano is known as complex. Complex, which means that it's harmonic. It's formed of a fundamental tone associated by other harmonic tones that are lower in intensity and higher in pitch. The types of sound waves, they are divided into two types. We have audible sounds which can be heard by the human ear, and another non-audible sounds which cannot be heard by the human ear, which means that the human ear can find or can hear some sounds and others cannot be heard. Audible or the sonic waves, they are the sound waves that are ranging their frequency from 20 hertz to 20 kilohertz, which means 20,000 hertz. Okay? The non-audible sounds, or the sounds that cannot be heard, they are like infrasonic, or they are divided into two types, infrasonic and ultrasonic. Infrasonic, it means that their frequency is lower than 20 hertz, and the ultrasonic, their frequency more than 20 kilohertz, more than 20,000 hertz. Okay? The infrasonic waves can be used to determine or to find the weather broadcast. Why? Because we can find some infrasonic waves that precede the storms, and also ultrasonic waves can be having another uses. But I'd like just to say a note here, ultrasonic waves which have a frequency higher than 20 kilohertz cannot be heard by the human ear, but we have other animals that can hear this ultrasonic. They are like bats, ducks, and dolphins. As dolphin can hear the frequencies of more than 50 kilohertz, so that it can hear higher sounds or ultrasonic waves. We have some useful applications for the ultrasonic waves. We can use them in medical field, as we can use them in breaking the stones of the kidney, and also in finding the tumors for the prostate gland in males. Industry also can be used, the ultrasonic waves, in sterilization of milk, as it has an ability to kill the bacteria. And the last use in military purposes, as we can find it to discover the landmines. Hope you study well and revise well. Good luck. Thank you.